Hey everybody, welcome back. This is part 5 of genetic algorithms, and in this video what we're going to do is look at mutation. Now, mutation it's not 100% necessary when you do genetic algorithms, and it really depends on the problem you're solving. Now, I would say you should almost always use it, but there might be some cases where it just adds unnecessary overhead. And the cases where it wouldn't add unnecessary overhead is when you have a really large space that you're searching for answers in. Now, the thing is if you had a smaller space, you probably wouldn't use genetic algorithms anyways. But for the sake of this example, let's say that you had, 10,000 possible solutions. You wouldn't actually use genetic algorithms to solve that. You just search all 10,000 possible solutions. But if you had 1 trillion possible solutions, and you're going to use genetic algorithms to try to find a really good solution within that, well, mutation can help you do that, because you might start with an initial 10,000 chromosomes for your genetic algorithm to solve this problem with 1 trillion possible solutions. So you start with that, the initial population gets mixed up in selection and reproduction, and maybe it's not really getting enough variety. It's not, you can't mix up the initial population to cover enough of the variety in those trillion possible solutions. And that's where mutation comes in, because what it does is it kind of, changes some things here and there and pushes the variation in your genes or chromosomes away from the initial population. So it gives you enough variety where you're going to hopefully find a good solution. All right, so mutation, the basic idea is this. We take in our backpacks, in our case. We're going to assign it this floating point value, which is just 1% in our case, which means about 1 out of every 100 of the genes, or 1 and zeros, is going to get flipped or changed. I'm going to send in strand length, population size. Okay, so let's go ahead and create it. I've got reproduction here. We do it right below, mutation. We've got our backpacks, mutation rate, strand length, and population size. Okay, so actually I think this is probably of the three, this is definitely the simplest of the steps. Because all we're going to do is we're going to say for every backpack index in the range of the population size. So we're going to loop through every backpack or every chromosome, every strand of DNA, and we're going to look then at every gene within each of those backpacks. And all I'm going to say is if random is less than or equal to mutation rate, then I'm going to flip it from 0 to 1 or 1 to 0. So random is something we need to include, and it's actually a function from the random module, and all random does is give us a number between 0 and 1. So we're going to hope this will give us enough where about 1% of the time we're going to want to flip it. So let's take a look at how we're going to flip it. So what I'm going to do to flip is I'm going to say, get me the backpack, that location, then get me the gene at an individual location. If this random is less than 0. Or equal to 0.1, I'm going to change this value like this. Okay, so what this says is if backpacks is 0, if this gene in the backpack is 0, I'm going to add 1 to it, which gives me 1, and 1 modulus 2 is just going to be 1. Now, if it happens to be 1, if it's a 1 as that gene, then 1 plus 1 is equal to 2, and 2 mod 2 is 0. Okay, and that's it. That's all you have to do for mutation. This is a very simple form of mutation. There's other ways to do it, but I'm just going through looking at individual genes, and I'm just changing them if it happens to meet the conditions for the mutation rate. And when I'm done, I can return those backpacks. And there we go. That is all 3 steps: selection, reproduction, and mutation. Let's go ahead and print out our backpacks. right, there we go. And you'll see that, I mean, it still looks kind of like what we had before. There's not really anything interesting in here. It's just all seemingly random. You'll even notice that at some points I probably have illegal backpacks. And that's because after I do mutation, I might have flipped some zeros to be ones in cases that made it an illegal backpack. So actually what you'll want to do before you have a solution is select one more time. Okay, so that will get rid of all the overweight backpacks. The other problem is we've only done one cycle, and that's not really going to help us find a solution. So we need to do this multiple times. So we need multiple generations. So I'm going to say for generation in range 10, for example. And since we have such a small problem here, only 6 genes, just 6 items in these backpacks, we don't need to actually do a whole lot of cycles. So let's take a look at if I just do 10, and I think you'll see something kind of interesting. So, all right, here it is. So we've got all of these backpacks here. Now you're gonna notice almost all of them, except for those last ones at the end, it seemed like there was a lot of mutation down here at the end, which is kind of interesting. But up here, all of these are the exact same backpack. So what's happened is all of the chromosomes, everything in our population has kind of got pushed to be the best it can be, because that is the best possible backpack. If you look here, we've got 2, 3, and 7 for the weights. So that'd be 2, 3, 7, which is 12. And the cost are 6, 7, and 3. And they're the highest cost of all 6 of these in here. So obviously those are the 3 you're going to want in. And that's exactly what we have. So the highest cost, or the highest valued backpack would be 16. And the weight is going to be 12. And these last backpacks down here, they're just some mutations. And it looks like we just flipped a couple and flipped a couple. If I run this again, you'll get something similar. Oops, what did I change here? Oh, let me try to run it one more time. There we go. That last one was kind of interesting. Maybe. So that last one had the ones at the beginning. See if I can get that again. There we go. So sometimes you're going to get these solutions which are incorrect. Not incorrect as in they're invalid, but you notice it's actually taking these. This is also a valid backpack, 111. And it's not as much. It's 1 less than the cost of this one. And that can happen sometimes, because when you are only doing 10 generations, and it might get stuck in what is called a local minimum. And this is a local minimum as opposed to the global minimum. So this local minimum, or the local maximum, in this case, be the highest value we want to get. And so we might have had a lot of backpacks in that initial population, and they would have been a very high probability for getting chosen again, not as high as the other one, but they would quickly reproduce the other ones. Now, if I run this 100 times, it's very, very unlikely. You might see it here a few times. Most of the time, I'm going to get those 3 on that side. Every once in a while, it gets stuck over here. And that's a problem with genetic algorithms. You're never really guaranteed to find the best solution. You're guaranteed to find a good solution, but not the best one. All right, so play with this code a bit. I'll just give you a couple more examples here. Like if I up the weight, for example, to 20, you're going to see that it's going to take all 4 of these, which makes sense because this is the lowest weight of the last 3 remaining, and then it also has the highest cost. If I were to maybe put this at 30, you're going to get 5 different things in there. It's going to exclude this first one because it's just worth 1. If I put this at 10, well, I'm going to get something that's slightly different. I get 10, and it's going to include this 5. It's going to include 2 and 3, and then actually include the 5. And so that's a time when 5 actually would matter, even though it's the lowest cost here. So there's a lot of different things. Play with the max weight. See how that changes the output. In the optional video after this, I'm going to go ahead and add some additional stuff on the weights and the cost, and show you like how to make random chunks of data, sample data, and how you might get some errors and what you can do in order to fix those. All right, so if you have any questions about this, please leave them in the comments. Otherwise, you can take a look at the code, which should be linked below on GitHub. All right, thanks for watching, and see you next time.